In section 2.4, we're going to talk about end behavior. So end behavior is what happens when our function gets very large or very small. So first thing we're going to talk about is this limit notation that we're going to use. And then after we get a grasp of that, we're going to talk about finding these limits both graphically and numerically. So let's start with what this limit notation means. Okay, so over here we have the graph of negative x to the third plus 27x. Alright, so what we mean by end behavior is what happens when my inputs increase, right? So the input, that would be the x-axis here, as the inputs increase, bigger and bigger and bigger and bigger, 4, 5, 6, 7, and so forth, we're going to move along the graph to the right. Okay, so as the inputs increase as I move along this graph to the right, well, what happens to my outputs, my y values? Well, my y values go up for a minute and then go down. Here I'm probably negative 100, negative 200. Well, the outputs then decrease. So here, as the inputs increase, the outputs decrease. Okay, another way to think of that is as my inputs increase, as I move to the right, the inputs are right and left, the outputs decrease or they go down. Alright, so I don't think that's a tough concept. What is a little cumbersome is the notation we have down here. So this is our limit notation. The mathematical notation for this is given by this. So the way this is read is the limit as x approaches infinity of f of x is negative infinity. Alright, so this part under the limit symbol right here, this tells us whether we're going to the left or right to find that limit. Okay, because see, this is the inputs, the x's here. Alright, so in our case, x approaches positive infinity. X gets bigger and bigger and bigger and bigger and bigger and bigger. So this would be as x approaches positive infinity. In this case, we're going to the right. Alright, so as we move to the right on our graph, well, what happens? Do we go up or down? So this piece right here, the result of this limit tells us if we are going up or down. Alright, now in our case, as I move to the right, I'm going down. Right, so we are going to have a negative infinity. Okay, so the concept I don't think is difficult. What gets cumbersome is I have two different infinity symbols meaning two different things. So under the limit symbol here, under the limit symbol, if I approach positive infinity, I'm going to the right. If I approach negative infinity, I'm going to the left. Alright, and then my result over here, if my result is negative infinity, I'm going down. If it's positive infinity, I'm going up. Alright, so let's see if we could look at the other limit for this function. So here, as the inputs decrease, so as my inputs decrease here, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, we are moving to the left. Okay, so as my inputs decrease, as I go to the left here of my graph, well, what happens to the outputs? The outputs increase. Right? Do you see I'm going up here? The outputs are going up. Alright, so let's see if we could use that limit notation. This piece down here, underneath the limit symbol, says when we go to the left, forever and ever and ever, as x approaches negative infinity, as my inputs go to the left, well, here we are going up. So we were going to represent that with the positive infinity. So again, under the limit sign tells me left or right. The result over here is telling me whether I'm going up, positive infinity, or down, negative infinity. Now there is one more case where we level off, but we'll talk about that in a minute. Alright, so let's see if we could use this limit notation to find both limits for these graphs here. Alright, so here, as I go to the right, I am going down. So as I go to the right here, we're going down. Alright, so how might we represent that? We're going to say the limit underneath the limit symbol as x approaches to the right would be positive infinity of f of x equals, well, we're going down, so we're going to use a negative infinity right here. Okay, now let's do the other limit. As we go to the left here, well, I'm also going down. So this says as we move to the left, we are also going down. Okay, so the limit as x approaches the left here would be negative infinity of f of x is down is also negative infinity. Alright, so let's look over here. As I go to the right, I'm going up. Alright, so we'll say the limit to the right as x approaches positive infinity of k of x, well, we're going up, so that is also positive infinity. Alright, now let's see, as we go to the left here, I'm going down. Okay, so the limit as x approaches left would be negative infinity of k of x is down would be negative infinity. Alright, and then g of x over here, as I go to the right, I'm going up. So the limit to say right as x approaches positive infinity of g of x, and then up is also positive infinity. Then as we go to the left, I'm also going up. So the limit as x approaches left is going to be negative infinity of g of x. Up is positive infinity. So this is our limit notation as x increases or decreases without bounds. So we could end up going up, going down. Now there is a third case in which we might level off. All right, so Sometimes when I go to the left or the right, the outputs get very, very close, but don't actually reach a specific value. They kind of level off here. Okay, so if we get really close to a specific number, I'm not going up, not going down, I kind of taper off, we might have what is called an asymptote. Asymptote. All right, now I guess that should be an and, shouldn't it? Has an asymptote. All right, so these asymptotes are not actually part of the graph. We just represent them to help add them in to help us understand what's going on. So consider the graph of 5 times 0.75x to the plus 5. Now as I move to the right here, do you see that I'm going to taper off and it looks like I'm getting really, really, really close to 5 here? So it appears as the output values get really, really, really close to 5 as we move to the right. So instead of going up or down, we're tapering off to 5. So I might write that the limit as x approaches infinity, right, as I move to the right of g of x, well, I'm not going up or down, I'm tapering off to 5. I'm going to get really, really close to 5, but I will never actually touch it. Now to represent that, we use this dotted line here. This is the asymptote. Alright, so this isn't actually part of this equation here, it's just showing us that we're getting really, really close to that number 5. Now the equation of the asymptote, this is a horizontal line here. So the equation of that asymptote, which isn't part of our graph, it just helps us understand what's going on. Because it's horizontal, we're going to use y equals, and then that's the number 5. Again, if it was a vertical asymptote, you might use x equals. Alright, so let's see if we could describe the end behavior of what's going on here using our limit notation. So as we go to the right here, this tapers off and gets really, really close to 2. Alright, now I didn't tell us whether these are f of x or g of x, so we're just going to call them all f of x, let's say. Alright, so the limit as x approaches positive infinity, as I go to the right, we get really, really close to 2 here. Okay, if I go the other direction, if I go to the left as x approaches negative infinity, well, as I move to the left, it looks like we're getting really close to this asymptote here at negative 3. Okay, well, let's call this one g of x because I forgot to tell us. Alright, so on g of x, as I go to the right, we get close to this asymptote here at 2. So the limit as x approaches infinity, as I go to the right on g of x, I'm going to get very, very close to 2. Okay, as I go to the left, well, here we're not tapering off, we go up. So we're going to have to use that notation from the beginning of the video. As x approaches negative infinity, as I go to the left, well, here we're going up. So we're going to use a positive infinity. Okay, and then lastly here, as I go to the right, I'm getting really, really close to this dotted line here at, that looks like negative 2. And as I go to the left, I'm also getting close to that asymptote at -2. So what are we going to call this? Let's call this h of x, because I forgot to tell us. So the limit as x approaches infinity of h of x is -2. And then similarly, as I go to the left, so underneath my limit sign, I'm going to have a negative infinity of h of x is also -2. Okay, so this first example here had 2 horizontal asymptotes. The second example here had 1 horizontal asymptote, and the third had a horizontal asymptote and a vertical asymptote. Alright, now next we're going to talk about how we would find these limits. I'm going to use that same limit notation that we just talked about, but numerically, meaning I don't give you the picture, I give you an algebraic expression, I give you an algebraic representation, and we're going to use the table menu to try to figure out what's going on here as I go to the left and to the right. So the first thing we're going to do is enter our equation into our table menu. So I'm going to hit menu and then go to my table menu. I have some old stuff in here that I'm going to delete, and then I'm going to enter the equation in here. 1 plus x to the -1, then close my parentheses there, to the x. Alright, now we could set our table menu up as we have here, but I'm just going to type over these. So once I get my equation entered, I have to hit execute to save it, and then F6 to view the table. Now the numbers that I have listed here are 5, 50, 500, 5,000, 50,000, which are not what is displayed here. However, I can just type over these numbers. So I'm going to type 5, and if I go out to maybe round to 3 decimal places here, this gives me 2.488. Okay, now I'm going to move down here and type 50, and I get 2.692. Alright, then we're going to go 500, 2.716, 5,000, 2.718, so it looks like this one's tapering off. And then let's try 50,000, 2.718 again. So it looks like it's tapering off to about 2.718, but I'm going to go one more time. Let's go 500,000 just to make sure. Yeah, 2.718. So it looks like as my inputs get larger and larger and larger, this is tapering off to about 2.718. So the limit notation that we would use there would be the limit. Now our x's got larger. We went to the right as x approaches infinity of f of x. And if we round to 3 decimal places, we get 2.718. Alright, now let's see if we go to the left what we get here. So I'm just going to go back, and instead of putting 5 here, I'm going to put -5. Alright, I get 3.0 0.052. All right, then negative 52.746. All right, negative 500, 2.721. Negative 5,000, 2.719. And then negative 50,000, 2.718. Now this one we might need to go a little bit further. It looks like it's tapering off to the same number as the positive limit. But let's go one further just to make sure. Negative 500,000. Yep, it looks like we're getting close to 2.718. Okay, so we say the limit, this time we went to the left, as x approaches negative infinity of f of x is also 2.718. So we're using the same notation as before. What's different is we're using a numeric representation as opposed to a graphical. Alright, so let's look at a couple examples here. Now, here I didn't give us the table. We're just going to enter larger and larger numbers and then smaller and smaller numbers into our table until we can figure out what's going on here. So I'm going to enter my equation into my table menu. Okay, and we aren't given any specific values. I could use the same ones as before, or let's start with the right. Let's say 10 maybe, 100, 1,000, 10,000. All right, now what's going on here? We start off with 10. Now here, do you see this is scientific notation? This is 3.52 times 10 to the 6th. Now, if I look down here, do you see this gives it in this notation we're more familiar with? Do you see this is getting quite large? Well, then the next one is 1.4 times 10 to the 61. All right, so I'm going to take this decimal right here between the 1 and the 4 and move it 61 times to the right. Do you see that number is very, 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 very large? Okay, and then next I get an error. Now why might we get an error? Well, do you see if this number has 61 points in front of the decimal, that this is probably so large my calculator can't even handle it? So it could be that I got too large too quickly. Maybe instead we'll do 50, 100, 150, 200. The pattern might be more obvious if we don't get large so quickly. But do you see that these output values are getting very, very large, right? If 3 to the, let's see here, if I move this 6 places to the right, we'd get about 3 million. Then this would be about 3.8 billion, and this would be 4.1 trillion. So this is getting very, very large. So the way we would represent that the limit as x approaches infinity as I go to the right of f of x, well, those numbers got really, really, really large. We had to use scientific notation to represent them. So we're going to use positive infinity here. All right, now let's do the same thing to the left. All right, so maybe we have negative 50, negative 100, negative 150, negative 200. All right, and it looks like these are getting very, very, very close to negative 2. So it tapers off to the left. So the limit as x approaches negative infinity of f of x is getting very close to negative 2. All right, so let's try the next one. I'm going to exit back. Now, the absolute value symbol, we find that under options. So first I'm going to put my negative here. Then to get the absolute value symbol, I hit options. Then we're looking for our numeric menu. And there's absolute value of x. And then we close those parentheses, and then we want to add 3, I believe. Is that correct? Yes. All right, so as I go to the right, let's try 10, 100, 1,000, 10,000. It looks like these values are getting very, very small, right? They're getting, so as I go to the right, I'm going towards negative infinity. So the way that we would represent that is the limit as x approaches infinity. I entered larger and larger numbers. I went to the right. Then the outputs got smaller and smaller and smaller, which would be represented with a negative infinity. Okay, so now if we go the other direction, I'm going to enter very, very small numbers here. So maybe negative 10, negative 100, negative 1,000, negative 10,000. It looks like those also go down. 100,000. Alright, so as my inputs go to the left, as they get very, very, very small, my outputs also get very, very small, so they go down. So the limit as x approaches negative infinity of g of x, those are the values that I entered that got quite small. Well, the outputs also got small, negative infinity. Alright, now this one's going to be very important here, that when we enter this, we have parentheses around both our denominator, and I want you to enter parentheses around your exponent. So let's see if we can get that one in our calculator correctly. 5 divided by, open the parentheses for my denominator, 1 plus 2, raise that to the power, open parentheses for our exponent, negative x. Now I'm going to close them for my denominator, and then minus 3. Alright, so let's see what's going on here. Maybe we try, well, what were we doing before? 10, 100, 1,000? 10, 100, 1,000, 10,000. Looks like those are getting really, really close to 2, I believe. Alright, so we're going to represent this, the limit as x approaches. I entered larger and larger values, right? I'm moving towards the right of k of x. And those numbers got very, very close to 2. Okay, if we go to the left, let's see what happens here. I'm going to enter -10, -100, -1,000, and I get an error. Now, why is that? This is probably more than the calculator can handle. Let's try -10,000. Alright, so what I'm thinking is happening here is I got too small too quickly. So let's try, I'd hate to make this judgment off of just those numbers. Let's go a little more slowly. Let's go -50, -100, -150, -200. Alright, so it looks like this is getting really, really close to -3. But if I got too small too quickly, the calculator overflows, so it can't handle that value. Alright, because we end up dividing by something that's very, very, very close to, no, it's very, very, very large there. Okay, so the limit as x approaches -infinity, because we entered very, very small values in, got very close to -3. Alright, and lastly, let's try the cubed root of x. Now, to get the cubed root button, you see it's in yellow here above the left parenthesis, so you have to hit Shift, the left parenthesis, for the cubed root of x. Alright, so let's try 10, 100, 1,000, 10,000, 100, 1,000, 1,000,000. Alright, now, oops. It looks to me like as these get larger and larger and larger, these also keep getting larger and larger. They're not tapering off. So as I move to the right, this is going up. So our notation for that is the limit as x approaches infinity of h of x. Well, those numbers are also getting larger. So we're going to put positive infinity there. Alright, and let's do the same thing to the left. -10, -100, -1,000, -10,000, -100,000, -1,000,000. Yep, those are now, as I move to the left, as I enter smaller and smaller values, these values over here are also getting more and more negative. Alright, so the limit as x approaches -infinity of h of x, because we entered smaller and smaller values, well, those values are also more and more negative, so we get -infinity as our limit. So that's how we can find these limits numerically.